there, and welcome to part 4 of our mini-series on doing theoretical research, all with the triangle. And by the way, you deserve a prize if you figured out that I've been wearing the same shirt for like videos on end. But here we go. We left off last time with this equation. X is equal to 1/57th a theta in degrees. We're feeling pretty good about this equation, but how well does it really hold up? I've been hiding something from you, which is that we haven't really considered values of theta bigger than 60 degrees. And it turns out if you start calculating best values of f when theta is bigger than 60 degrees, approaching 90 degrees, that all those best values for f become not only different from one another, but from the old values of f that we were calculating. This means that our triangle can be understood by our theory only when theta is small enough. Limitations like these are common when constructing theories. For example, Newton's law of gravitation works to a point, but it doesn't work out in all the ways that Einstein's theory does. There are things that Einstein's theory predicts that Newton's law doesn't. Also, under the right conditions, Einstein's theory boils down to Newton's law, just like how a more complete theory here would boil down to our equation, with a small enough angle theta. There's another important thing we haven't addressed yet, which is that we've assumed from the start that we can multiply the two quantities of theta and a together, scale it by a number f, and get the right answer. While this has worked out up to this point decently well, we've limited ourselves by this assumption. Story time! I was once working on a project in something called synthetic biology, where you're re-engineering bacteria to do things for society or science and engineering, etc. And I was modeling how bacteria would interact in the human lung. And yes, the human lung has bacteria. It has it already. Long story short, I had to make a decision. Do I treat the lung like the really complicated shape that it is to figure out exactly how these bacteria might interact? Or can I assume something more simple and capture still the majority of the reality? So I assume that you could model the human lung as a cube for our purposes, and I never looked back. Don't worry, it worked. I think. End story. The point here is that reality is often, if not always, more complicated than the math used to model it. But you can still do a good job at capturing what it is, as long as you make reasonable assumptions and you check those along the way. Anyway, what exactly is the more complete theory here? And how do we stack up? To find out how well we did with our equation, let's compare the actual trigonometry of the situation with what we've done in our next episode.